Good evening once again. So for today's meeting, we're continuing with the some of the very important philosophical perspectives of probability. In the previous session, we talked about the classical school of thought or the classical perspective of probability. And we did agree that when it comes to the classical thought, we're thinking of probability as from a more a priori standpoint. Okay. Even before the performance of the experiment, we're able to compute certain probabilities, and we looked at it from the perspective of favorable events as a proportion of the number of events in general in our sample space. Okay. And that we dovetailed into considering probability from a combinatorial standpoint. And for the combinatorial standpoint, we did indicate that, so for example, if there are some n objects and we have m of them being of a certain type A, then we can compute the probability of selecting, say, some r objects of that type A. And we did agree that that probability of a type A would be the M combination R as a proportion of N combination R. Okay. Where of course N combination R gives you all the various, combinatorial possibilities, so to speak. All right. However, we can look at probability from a more empirical approach, right? Or what we call a posteriori approach, in which case we can only ascertain what the probabilities are following the performance of the experiment. All right. So the consideration that we're giving for today's meeting is we're looking at the frequency school of thought of probability, and then we'll also talk about the subjective, okay, because there are three in all: classical, which we've talked about earlier, the frequentists dimension, and then the subjectivists perspective as well. All right. So in general, the relative frequency approach, all right, overcomes the disadvantage of the classical approach by using the relative frequencies of past occurrences as probabilities. And this approach claims that the only valid procedure for determining event probabilities is through repetitive experiments. All right. And so with that as an opener, let's consider this. Let's put a few formal statements down. So let's do some writing here. So we're considering the relative frequency. All right, the relative frequency, or what we call the frequentist school of thought. All right. So we can begin by saying that suppose that an experiment is repeated, all right, or performed a large number of times. All right. Of course, under the same conditions, that goes without saying, under the same or identical conditions. All right. Then there are some specifications with each of the n trials being independent of another, being independent. All right. Then we can say that if the event A, right, if an event A is observed to occur in how many elements, or yes, what's the size of event A? How many members belong to event A, right? So in the trials. Okay, so you have n of A of the trials. Then the argument is the probability of the event A. The probability of the event A is giving us, so let's call that some R of A, which is still a probability anyway, but we're just using R to show that there's relativity. All right, so R of A or P of A is given by, or the relative frequency, okay? The relative frequency of A is essentially the number of items that have the property A divided by the total number of items there are. Okay, so this is going to be number of A over what? N. So for example, if we say that what's the relative frequency of males in a class, it's going to be the number of males divided by the number of members of the class. If we talk about the relative frequency of females, it'll be the number of females in the class divided by the total number of students that there are in the class. All right. And so this will be that probability. All right. So we're looking at probability from a relative frequency standpoint. So, if we want to explicitly indicate that the event A depends on the number of trials, okay, then we will be writing something like this. We'll be writing R subscript N of A. The different probabilities for different number of trials stabilize, or they approach a certain limit as the number of trials or experiment increases. Okay, and a way of just writing down that statement is to say this. So let me write it here. So we have Rn. Okay, Rn is the relative frequency of the event A, and we're saying that it depends on the number of trials. All right. So what we're just saying is if we perform the experiment a large number of times, so when n grows, so this is what I mean. When the limit of Rn as n approaches infinity, when we take that limit, all right, this is the same as, we know what Rn is. Rn is n of A over n. So we have n of A on n. And this is our probability of A of interest. Okay. So this is just to mean that so this implies that just as a quick, note, this would mean that the event A, all right, so events A depends on the number of trials. Or is a function of the number of trials. Okay, but it is the same as the R of A. But sometimes we want to be extra explicit that the event in question depends on the number of trials. So we're saying that if we want to find the probability from a frequentist standpoint, we just take the limit of the relative frequency as the number of trials gets very large. That's what the statement means. So this limit, all right, this expression, all right, this means that when the number of trials increases without bound, all right, or when the number of trials gets large, that's how we write that mathematically. So the limit as n approaches as n approaches infinity. So this type of limit is what we call the probability limit. And the P of A is a unique number to which the outcome ultimately settles. So this means that when n is very large, the ratio, okay, as n gets very large, the ratio may be taken as an approximation to the true probability function that underlies the experiment, in the sense that Rn of A will become close to P of A. All right. And you see, this assertion is not just about mathematical limits, but more about empirical phenomena, right? I mean, there is no way to actually repeat an experiment an infinite number of times to evaluate the limit. But the intuitive idea or the intuition is that such a limit would exist. All right. It is obvious that with the relative frequency approach, there is just no way of estimating the probability without empirically drawing a sample or performing the experiment. And it's for this reason that the frequentist approach is what we call the empirical approach. All right. So the frequentist approach when you think of the frequentist school of thought, think about empirical. Or the posteriori. You remember the classical thought was a priori because we can determine the probability before performing the experiment. This we can only determine after we have performed the experiment. So post, okay, so post or posteriori or posterior. All right. We may therefore describe the frequentist approach as being wise after the event. You remember when we talked about the classical, it was being wise before the event. In other words, being armed with the information about the probability before we perform a certain action. But for the frequentist approach, you can only get wiser or become informed after the event. Okay, so the relative frequency definition is also objective because the probability of an event is determined by repeated empirical observations. Okay, but the key important thing to keep in mind is that the the n of a over n, this ratio is only an estimate of the p of a. All right, it's only an estimate of the p of a. Let me just give a quick example before I write down a few of the properties. So in the case of for example, if you have a coin and we're tossing the coin, right? If you wanted to determine the probability by the classical approach, all right, by the classical approach, so let's draw a quick table here. So by the classical approach, by the classical thought, we're looking at, first of all, how many possibilities are there when you toss a coin, right? So there are two possibilities or two possible outcomes, so divided by two. And how many, if we're interested in the head, how many heads are there in the first place? There's only one. Okay, so the probability is one favorable event over two possible outcomes, and that gives you two, right? But when it comes to tossing the coin and trying to ascertain the probability from a frequentist standpoint, we cannot do this. What would happen is we need to perform the experiment a large number of times. Okay, so our n has to approach infinity. So what would happen is this. So frequency. Okay, so what would happen is if we're still trying to perform that experiment, okay, we want to find the probability of, let's say, a head or the probability of a tail. It means that we need to perform the experiment a large number of times. So under the frequentists, what would happen is we have the number of trials, we call it n, and then I'm counting the number of heads and then the number of tails. All right. So when I perform the experiment, let's say I toss the coin one time. So n is equal to 1. What did I record? Was it a head or a tail? Let's say we got a tail. Let's perform the experiment a second time. 2. All right. Maybe we got a tail again. Let's perform the experiment 3 times. Maybe we got a head. Let's perform it 4 times. We probably got a head. 5 times. We probably got a head. So let's perform this a large number of times, maybe even 1,000 times or 10,000 times or 100,000 times, right? If it were to be possible. So 1,000 times, maybe 100,000 times. And we can do all these things by simulation, okay, computational simulation. Maybe even 1,000,000 times. Okay, the idea is, regardless, you would observe that on average, okay, you would observe that on average, the relative frequencies approach 0.5. Okay, so for example, if you compute all the sum of the number of heads that we've had, okay, so at the end of the day, you would compute the number of heads, and you may have, for example, if we perform the experiment 1,000 times, on average, regardless of the dynamics, it's possible that the number of heads, right? The number of heads may be out of 1,000 times, we probably had 495. Okay. And then maybe the number of tails, we performed the experiment 1,000 times. So 1,000 minus 495, that is what, 505. Okay. So the frequentists or the relative frequency approach is saying that we can compute the probability of a head. Okay. If we take the limits as the number of trials approaches infinity of the number of heads all over the number of trials. All right. So this is more or less taking the limit as n approaches infinity of the number of heads over the number of trials is going to be 495 over 1,000. And you'll see that this side becomes what? About 0.495. Okay. If we compute the probability of a tail, it's also going to be the limit as the number of trials gets very large. And then we'll take the frequency, the relative frequency. So number of tails over number of trials. And there's going to be the limit as n approaches infinity of 505 over 1,000. All right. So you'll see that here, this is the limit as n approaches infinity of about 0.495. And this is also taking the limit as n approaches infinity of 0.505. So as n gets very large, all right, as n moves from 10 to 100 to 1,000 to 200,000 to a million or even plus, this 0.495 will get closer and closer to an average value of 0.5. And this 0.505 would also get closer and closer to 0.5. So at the end of the day, when n gets very, very, very large, all right, when n gets very, very large, all that we're saying is that the number of heads, so as n gets very large, okay, the ratio of the number of heads to the number of trial would approach 0.5. And the ratio of the number of tails to the number of trials would also approach 0.5. So that given the two, you get 1. We can apply the same reasoning to rolling a die. Okay, so you can create a column, a table where you have a column for the number of trials and the various outcomes. All right, so that would look something like this. So when you roll a die, it means that here you have what the number of trials, and then you have the number 1, 2, 3, 4, 5, and then 6. So you perform the experiment one time, you roll the die. What did you get? Maybe you got a 3. Another time, what did you get? Maybe you got a 6. The third time, maybe you got a 1. if you perform this experiment a large number of times, or when n approaches infinity, and you take the relative frequencies, okay, the number of ones divided by the number of trials, the number of two divided by the number of trials, the number of threes divided by the number of trials, the number of four divided by the number of trials, the number of five divided by the number of trials, the number of six divided by the number of trials. All of them would approach 1/6, or the decimal representation, right? Each one of them, each of those probabilities would approach 1/6. Okay, so that when you sum all of them, you get exactly one. So that's the whole idea of the relative frequency approach. So the key argument to keep in mind is that the n over a over n is an estimate. It's an estimate of the probability of A. All right, that's the core idea that you need to keep in mind. So let's consider some important properties. So properties of the frequentists or the frequency approach. Okay, so number one, we can say that 0 we can say that Rn, okay, the relative frequency of A, that ratio is bounded on 0, 1. All right. So this means that 0 would always be less than or equal to Rna, and Rna will be less than or equal to 1. Right? So this means that if you perform the experiment or the trials and A occurs in none of them, so if A occurs in none of the n trials, then if A occurs in none of the n trials, then it means that Rn A okay, Rna becomes and A occurred in none of the trials. So the number of elements that are characterized by A is 0, right? So you get 0 over n All right. So when you would always have a relative frequency of 0 when A occurs in none of the trials. So for example, if we roll a die and we never get a 6 throughout maybe the 1,000 times that we roll the die, then it means that the relative frequency of a 6 would be 0. Then on the extreme end, if A occurs in all of the n trials, then the relative frequency of A, which is the number of elements bearing A over n, becomes, then it means that if A occurs in all of the n trials, it's like saying that we roll a die, maybe we roll it 10 times, and in all the 10 times, we get a 6. So the number of sixes is what? 10. So you end up getting 10 over 10, and that gives you 1. All right. So the number of A would always be n, and then you end up with a 1. Okay. But in most practical cases, you would be between the 0 and the 1. Right? You would always be between the extremes. All right. So, I mean, given this, right, we can also rewrite it. So we can also write this in terms of the actual probability. All right. Since Rna is what? The number of A over n. It implies that the this boundary 0 less than or equal to R and A is less than or equal to 1 is all right, is sort of equivalent to saying that 0 is less than or equal to n A over n is less than or equal to 1, which means that then 0 is less than or equal to NA, and NA will always be less than or equal to N. So this boundary also means exactly this. Okay, and of course, we arrived at this by multiplying through the inequality by N. So N goes into 0, 0, N goes into N A over N, you know, the N's cross off, we're left with N of A, and then N going into 1 becomes what? N. Right? So that's the whole idea. So the second property is that given any two events, right? The number of elements in A or B.
Oh, Charlie.
The number of elements in A or B is the sum of elements in A and B after taking, all right, following which we take care of any commonalities or any intersections. All right. And of course, this is coming from, we can draw this Venn to just kind of illustrate that property. So these are any two events. So these events may be disjoint or non-disjoint. Okay. Let's look at the case where they are not disjoint. Not just disjoint means that they have overlaps. All right. So this is, let's say, A and B, right? This full circle is members of A, which may also include B, okay, because you can see there's an overlap. And this full circle on the right represents the members of B, right? So once there are overlaps, then it means that the number of members or the membership of A or B would be those in this whole circle, those in the full left circle, plus those in the full right circle. Okay, then we take out this part. Okay, that would give us the membership of A or B. But it could happen that, so this is the case of non-disjoint. So they are not mutually exclusive, right? Let's take the case of disjoint or mutual exclusivity. All right, so for example, if we take a coin toss experiment, it's not possible to have it's not possible to have a head and a tail occurring at the same time. If you roll a die, it's not possible to have a 3 and a 6 occurring at the same time, right? Good. But let's say if you take a real world scenario in the university, you could have students who are reading, say, statistics and computer science, right? You could be reading statistics and you'll be taking the university required courses, and somebody reading computer science would also be taking the required courses. All right. So those are common courses between both programs, statistics and then computer science. So it's possible to have those overlaps. All right. So we can also look at mutually exclusive or disjoint. So we have this. Then we have this. All right. So in such a case, this relationship would still be applicable. Okay. This expression would still make sense because we still have A people, we have B people here. So if we want the membership of A or B, so it's going to be the number of members in A plus the number of members in B minus the number of members in A and B. But here, because there are no members, okay, there are no members here. There are no members. So the number of elements in A and B would be 0. Okay, so you would see that if we move ahead, I can write this expression for both cases of disjoint and not disjoint. In the case where they are disjoint, it means that this side would go to 0. The n of A intersection B would go to 0 because there wouldn't be any intersection in the first place. All right. So we can say that we can therefore say that, so thus right? So here I'm invoking the relative frequency. So if the statement is true, I can also say the relative frequency of A union B is equal to the relative frequency of A plus the relative frequency of B minus the relative frequency of A intersection B. All right. So maybe I can write that notes. Notes that if A and B are mutually exclusive, okay, then this side, n of A intersection B would always be, or let me put it this way. Then A intersection B will be the null set, which will imply that the number of elements all right, will be equal to 0. Okay, and so we would have n A union B being equal to just NA plus NB. Okay, and by extension, the relative frequency of A union B would also be the relative frequency of A plus the relative frequency of B. Okay. So, I mean, we can take an example let's say if a coin is tossed 1,000 times and a tail comes up 508 times, if we want to estimate the probability of a tail, it's going to be the number of tails divided by the number of trials, and that's going to be 508 over 1,000, which is 0.508. Okay, and as I've talked about, the ratio 508 over 1,000, which computes to 0.508, is rather an estimate, but we'll be very reluctant to state that the probability of getting a tail on that coin is 0.508, because if we had stopped at some other number of trials, the ratio would have been different. All right. So again, the key word here is it's an estimate. So what we could say is that if we toss the coin many times, it would come up tail 50.8% of the times. Intuitively, we feel that as the number of trials increase, the relative frequency will settle down to some stable value, greater than 0, but less than unity, okay, or less than 1. That's the whole idea. Okay, but then, so based on what we've looked at so far, you would see that the relative frequency, or the frequentist school of thought, has some disadvantages, although it has some merits as well, right? The relative frequency definition of probability, number one, assumes that the conditions of the experiment are reproducible. Okay, this assumption may not be valid if time is one of the factors to be considered. So by this, I mean that the conditions under which the experiment was performed may not always be reproducible. Okay, so let's say if we start tossing a coin and the plan is to toss it 1,000,000 times, and we start this evening, right? Within the next hour or two, we would have to go and get some rest in preparation for tomorrow. Okay, maybe because we started this evening, when we're tossing, we're feeling dizzy because, sleep was approaching. And if we ended at, let's say, the 1,000th toss or the 1,000th trial, if we wake up tomorrow, all right, when we wake up tomorrow morning, okay, as the Lord wills, what happens is that who knows, maybe we would have obtained some renewed strength or some renewed vigor. And that may also affect the way that we toss the coin, and that would also impact the various outcomes, right? Maybe tonight we started, and because, we've had a very tiring day, we're just tossing tails and tails and tails and tails. But who knows? Or maybe if it's a die roll, we're tossing anywhere between 1 and 3. But from tomorrow, when we're more energized, then we would end up maybe recording a lot more sixes. So the conditions under which the experiment is performed may not be reproducible. That's the first disadvantage. The second thing is that different probabilities or relative frequencies for different numbers of trials or experiment will be obtained in an attempt to estimate the probability of the event, right? So I can talk about a lot more as well, but we also can say that the expression large number of times or large number of trials in the definition is very vague, okay, and it creates even more practical problems. In an attempt to reach this number, we may face the problem of costs in terms of money and time, right? Because if we say a large number of times, how large is large? Is it a gazillion, a quintillion? What exactly is large? Is it 1,000? Okay, so, and if we want to go very, very large, it means that, again, there will be constraints there, cost, time, energy, etc. And also the concept of relative frequency approach in defining probability is somewhat intuitive, which is a plus for understanding. But when it comes to rigorous development, like I said, it places a lot of constraints because we need to perform the experiment before we are able to assess even a tiny probability. Okay, so in spite of the limitations, the frequency approach provides a link between the outside world and the mathematical theory of probability that we study. And it enables us to construct probability models of natural phenomena and study them. If the past is any guide to the future, and if by and large nature is stable, then the method of assigning probabilities to real world situations should be considered. Okay, that should be something that we should care about. So in this regard, let's move on to what we call the subjectivist definition, okay, or the subjective approach to probability, or the subjectivist school of thought. So, sometimes we try to quantify the possibility of an event happening. And when we do so, we're only expressing our opinions based on our feelings, our convictions, our exposure, our experiences, background, and generally our degree of belief, okay, rational belief for that matter. It's not objective in the sense that it's not based on performance of any experiment or an actual scientific computation. It's purely based on our, like I've talked about, our own sentiments, so to speak, right? Subjective probability here, is so refers to the degree all right, the degree of rational belief by an individual that the event will occur. Based on all evidence available to that individual. Or we can also say that so thus that the subjective probability of A is a measure of confidence that a reasonable person assigns to the event A. Okay, so that's the whole idea of subjective probability. So, for example, I mean, somebody could say that tomorrow is a Monday and there'll be intense traffic from 6 to 10 a.m. on a particular or within Accra or within the city. If I make the statement, it's subjective probability. Well, in some case, it would not be objective because it doesn't cut across. There are still places, within the city where even on a Monday you will not necessarily find traffic. Okay, but if I say that tomorrow Monday there will be intense traffic from 6 a.m. to 10 a.m. within the city, it is subjective probability and it carries a certain amount of fact to it, though it's not going to be a universal truth. But I'm saying this based on every available evidence, okay? Because I've seen so many Mondays in the past, and most of the Mondays, maybe 95% of the Mondays I've seen in the past, including yourselves, would be characterized by serious traffic jam from 6, sometimes even 5 a.m., depending on where you're coming from. Okay, as early as 5 a.m. all the way to about 10 a.m. traffic intensity. So this is not objective, it is subjective. But even with the subjectivity, I'm saying it based on some reasonable amount of confidence. And that confidence is coming from available evidence or evidence that is available to me. The evidence available to me is data or information I have of past several Mondays. All right. I mean, times ago where there wasn't, we didn't really have sophistication in technology, right? Our forebears, who were mostly farmers and, livestock rearers and things like that. How did they know that, well, this part of the year is, we call it what, rainy season and then dry season, okay? The dry season and the wet season. How did they know? When at that time they were not so scientifically exposed. So they would say things like, okay, it's approaching this month. We should expect, heavy rainfalls. It's because at that point they had a knowledge base of previous years and the distribution of rainfall and the distribution of sunshine. Okay, the distribution of heat versus the distribution of cold. And over the past several years, they've now encoded in their minds that, okay, once you get to this side of the year, between this time to this time of the year, it normally rains. And between that time to that time of the year, it normally doesn't rain. Okay, so if, let's say, your grandfather some years ago told you that, well, it's going to rain from next month for the next 2 months, he was saying it based on a subjectivist standpoint, which may or may not be the case, right? And we say that may or may not be the case because think about it, even the concept of wet season and dry season, you may have noticed that in our time, it's changed significantly. Okay, when we're growing up, when we talk about wet season or rainy season, you are 98%, 99% sure. And it will happen 99% of the time that there will be heavy rainfalls. I mean, heavy rainfall for that whole period. But these days, even in the wet season, you see the sun showing off, its glory and scorching the sons and daughters of men, as if, and you wonder, is this really what we call the wet season? Okay, or the rainy season? And on the other hand, for seasons that we call the dry season, where you're expecting, the you are not expecting rains, is rather when you see a lot of rains happening. Okay, for example, last year, it rained even during times that we're not expecting. Okay, so that tells you that no matter how certain that we are, once it's a subjectivist probability, no matter how true it has been in the past or seemingly factual it's been in the past, there's still some degree of error in there. That's what we call it subjective, because it's personal. All right. Yeah. So that really is it about the subjectivist probability. Okay. So now that we've looked at that, I want us to conclude by considering the modern definition. Okay. Which is what we call the Kolmogorov definitions, or what we call the axiomatic definitions, right? Because even though all the three different conceptual approaches, and by that I mean the classical, the frequentist, and the subjectivist approaches, have been developed for defining and interpreting probability of an event. At the mathematical level, there is no disagreement about the probabilities, okay, and the computation of the probabilities of events. So a mathematically useful treatment of probability should lay a common ground, a baseline, so that everyone would be speaking the same language. Okay, because if I am seeing the world through a classical standpoint, you are seeing the world through a frequentist standpoint, another person is seeing the world through a subjectivist standpoint, we cannot make progress. Okay, for civilization to move forward, for technologies to develop, mathematicians and statisticians, okay, we need to speak a common language of probability. All right. And so we have a Russian, mathematical statistician whose name is Kolmogorov, okay, sometime in the 1930s, who laid down three key axioms or postulates for defining probability. So when we say axioms, these are essentially some conditions that need to be obeyed or that need to be adhered to for a particular phenomenon to happen, right? So let's look at the axioms of probability, or axiomatic definition. Okay, so let's start with a preamble. So there are three core axioms. Okay, so we can say that let omega be a sample space. Okay. With elementary members E1, E2, and so on and so forth. Okay. And let's take an event A. A being a subset of the omega, right? It's an outcome. So of course it's a subset. It's contained within the omega, the sample space. Then let's define a function, which really is a probability function. Okay, so we can say that define a function okay, a function p, and p is such that p moves from, when p acts on omega, it takes it to, so I think let me write it on the other side. So define P. Okay, such that P takes the domain of this P is the omega, and this goes all the way to some value bounded on 0 and 1. Okay. Then the function P acting on the event of interest A, all right, is considered as a probability function. All right, if it satisfies the following three conditions or characteristics. Or what we call axioms. Right? So number one is what we call non-negativity. Every probability or every probability function has to be non-negative. So this means that for every event, A, the probability of A cannot be negative. It can be 0 or more, but bounded on 1. Okay. So for every event A, the probability of A should be non-negative. Non-negative means, as the name depicts, it cannot be negative. Okay, so it can be one, it could be more. Okay, then 2. So non-negativity, and then number 2, norm or normalization. Or normality. Okay. This means that the probability of omega should be 1. Okay, so sometimes the non-negativity argument, we write it so sometimes we combine the non-negativity and the normality argument. All right. So by 1 and 2, because sometimes in some texts you may not see 3 axioms, you will just see 2. But it's because the first 2 have been combined. So by 1 and 2, we can say that for every event A, okay, for every event A, we have 0 is less than or equal to the probability of A, which is just this, I'm flipping. And this should be less than or equal to the probability of omega. Okay, that is by 1 and 2, we have 0 should be less than or equal to the probability of A. It should be less than or equal to probability of 1. Then number 3. Finite additivity. Okay, so this means that if A and B are mutually exclusive, so if A and B are mutually exclusive, meaning if their intersection is null, then the probability of either events occurring, so the probability of A or B is simply the sum of the individual probabilities, because the probability of A and B becomes the probability of a null set, which gives you what? 0. All right. So that's pretty much it. So these are the three axiomatic definitions of probability. Okay, so meaning that whether you are a frequentist, you are a subjectivist, or you're a classicist, this is standard probability that all statisticians or mathematicians across the globe formally work with. Okay, just so that we can advance civilization. All right. So just to conclude, let's take a quick, maybe just some quick example to just really be sure that we've understood these building blocks. All right. So let's say that consider an experiment in which okay, the sample space consists of 3 elements. So let's call it E1, E2, E3, right? Which of the following or let's put it this way. So determine okay, and justify. So discuss whether each of the following functions defines each of the following defines a probability function of omega, right? So I'll give you the following functions of P. So we have number 1, P acting on E1 is 1/5. P acting on E2 is 1/2. P acting on E3 is 3/10. 2. All right. The probability of E1 is 3/4. All right. I'll be leaving this to you to go and think about. So the probability of E1 being equal to 3/4 is the first case. The prob of E2 Then number 3, we have the probability of E1 3 and 4 This is 1 on 2, and then 4. And then we have the probability of E3. Let's see, what value can I give to it? Okay, let's say the prob of E3 is 0. And then let's take number 5. The prob of E1 is, let's say, pi. The prob of E2 is, let's say, the Euler number, and then the prob of E3. The prob of E3 is the size of omega. Yeah. I think that should be just about it. And then maybe let's take this one. Let's take this one too. Okay, so this is A, B. And here, when I say discuss, of course, I mean it's a discussion. It's you need to write down your thoughts, but argue. It's supposed to be a mathematical discussion, right? Using the axioms of probability, right? So you take each one of the axioms and find out whether each of these 5 scenarios satisfy the 3 axioms. Okay, that's what I mean. I mean by discuss. All right. So let's take this. So this is A. So this is what I also want you to do. So this is the A. So this is question 1. This is question 1. And this is the A parts. Now the same question 1, okay? B. Okay, B, find P E1 and all right, find PE1 plus PE2. If PE3 is equal to 1/3 and 3 PE1. Okay, is equal to PE2. So this is B1. And then find PE1. Find PE1 if P E2 E3 is equal to 2/3 and PE3 is 1/4. Right? So I guess these are the core examples that I just want you to take a look at. All right, these are very basic problems, so just consider them. All right, and you'll be asked to submit them hopefully in the next couple of days. I'll just make the specification known to members, and I'll look forward to reviewing your responses. So so are there any questions at this point in time? If there are no questions, then thank you very, very much for your time, and I look forward to the next engagement on probability.